on these. And so we talked before previously about open channel flows or free surface flows, the phrases that we use synonymously. We've made the comment that it's completely driven by gradient, by gravity, gradient being the slope of the bed. And because we have this extra degree of freedom, and that is the depth of flow, which is kind of undefined in many respects, free for the free surface to choose, then we can get these interesting different flow configurations that we introduced last time, and that is defined in terms of the Froude number, which defines subcritical and supercritical flows. And so, like many things, for instance, in external flows, some of the examples are things like a hailstone falling through a cloud. Why is that lofted into the top parts of the cloud? Because there's an updraft, and it's gravity versus the drag, either pressure drag or viscous drag against that drop, and it is a balance between forces. And in the same way in open channel flows or free surface flows, looking at these kayakers, the balance here is between a flow which is going downstream, which is from left to right by the looks of it, and the balance again is between a gradient which is on the surface of this foamy wave, I guess upside down now, but back up again, and gravity pulling down. So drag against it being pulled up and gravity pulling down. And so it's this balance between these two forces. Viscous drag on the base of the boat, or it could be pressure drag, but probably viscous drag in this case, and also gravity going in the opposite direction. And so that's what's driving flow. And we did talk about hydraulic jumps. That's not the one I want, I don't think. This is the one I want. Again, hopefully with the volume turned off. And again, this configuration we know is that this flow on the left-hand side, by definition, must be fast, because the volumetric flow has to be the same, lowercase q as we used last time. So this flow has to be fast, and this flow has to be flow, just because of the cross-sectional area of flow that it goes through. And we'll talk today about how we can discriminate between these based on this idea of subcritical flow and supercritical flow that we introduced last time. So that's kind of where we're going today. So maybe I'll halt these. I don't know whether they're all playing, just in case they are playing. Still playing. Yeah, fine. And talk about where we are. So where are we? Well, we're here, I guess. We haven't gone through all of this, but we'll come back to it. But I think we'll do it in this order here. So let's see if I can make it full page. Get rid of this. I think get rid of this. Yeah, all right. So let's talk a little bit about where we were. We dealt with this a while back, and that is the simplest form. We were talking about gradually varying flows, and it's perhaps useful to recap where we were with that, because that leads into us being able to talk about these different behaviors. And so if we write it the way that makes sense, if we write Bernoulli's equation as upstream pressure, this is just in a different order from how we've written it in the past, V squared over 2G plus Z1. We won't put in the magnitude for pump head, and P2 again by unit weight. The velocity at a downstream location squared over 2G, the velocity head term, and the elevation component, plus a head loss. And so we've been used to writing that for, say, any particular geometry that we want, But the geometry that we want in this particular case is going to be flow in a channel. And that flow in a channel is between some upstream location here, and some downstream location here, relative to some datum. And so this would be our Z1, and this would be our Z2, which in this case would be 0 if we chose it. This would be our depth of flow, which we'll call Y1. And this will be our depth of flow, Y2. And related to this is this term v squared over 2g, which in general can be this amount here that has some slope to it. And these slopes, I guess we've called S0. This slope we've called S sub f. And physically, we know this amount as being this height h sub l, which is our head loss. This length over the flow length of our channel is lowercase l. And I guess these amounts here are v1 squared over 2g and v2 squared over 2g. So that's the fundamental relationship that we're working with. We're interested in writing it in this particular way because we know that we can write these terms here. If we take this flow line that's along the base of this region here, that this now becomes y1, this now becomes y2, and it's convenient for us to be able to group the other terms in terms of things that we know. And so this difference of z1 and z2 go together, because it's just a change in elevation. It's really the gravity that's driving this flow. And we could also write this one as C1 minus Z2 is equal to length multiplied by the slope of this base, which is this. And we can also write this term here as being HL is equal to the slope of this. I guess, did we use F or did we use something else for that? We did use F. The slope of this energy line, again multiplied by L. And so all this does is it allows us to write Bernoulli not in terms of abstract pressures and elevations and energy drops, but in terms of physical things that are present within the system that we can measure. And our modification of this was to write this in terms of a term which we called the energy upstream. Whoops, not that. These two terms as the energy downstream. And if we wanted to, we could rewrite this expression in a number of different forms. One could be E1 plus Z1, not rearranging this, is equal to E2 plus Z2. And we could write this in some way just as HL. Or we could write it as E1 is equal, or E1 is equal to E2 plus HL written in this way, L multiplied by SF minus S0, which is just taking these two terms and moving them around slightly differently. And this energy term, which is these two components, it's no different from these two components. What we chose to do was we chose to take our channel side on, that we can look at here, and we could define it in terms of a flow, not a total flow that we have in the channel, which we've always called Q, right? In terms of this geometry, if I can draw this properly, is that we take an amount which was just the amount flowing per unit width, which we called lowercase q, and we define this, if we have a channel width of b, as the fact that lowercase q is equal to the total flow rate, volumetric flow rate, meters cubed per second, divided by the width of flow. And if we did that, we know that this is going to be constant as we go downstream, so long as it doesn't constrict itself and it doesn't accumulate. And so in the same way, lowercase q would also be written that way, would also be constant. And so what we could do is we could write the velocity in terms of that. And if we did that, then we ended up with this value which we haven't defined. And we could write this magnitude of energy as these two terms, y plus q squared over 2gy squared. So this is derived, of course, from these two terms. This is the depth of flow. This would be, I guess, 1 in this particular case, and this would be 1, and likewise for E2. And so this is just really just this term which includes these two components, the pressure head and the velocity head, the inertial term. But we've substituted a velocity which would change potentially as you go up downstream because the depth might change, by a single term which will never change. So we know that we can get this magnitude here. We showed also that we could represent this behavior on a graph, that since we can define this behavior here, we could also write this as E1 is equal to this. And so in equating this to this term, if we have a given flow rate and we know gravity, then the only two terms we have in here are y1 and e, or y and e. And so if this is the case, we can always relate e as being equal to y plus q squared over 2gy squared. And what we did last time, I think, was we multiplied everything by y squared, right? So we end up now that you could write this as a quadratic. You could set it equal to 0, and just by rearranging it. And so by definition it has 3 roots. And so if we wanted to plot our behavior in terms of a diagram, which is an important diagram, which gives us depth of flow versus energy, which is equal to our E term, then importantly it's a quadratic that has some very particular features. There's a bounding line here which is at 45 degrees, which is y is equal to energy, as it turns out. And inside this bounding line, if you just choose a given value of flow rate and you choose a value of y, you'll get a value of E out of it. And so what you can do is you can choose a flow rate. So this would be Q equals constant. And you'd end up with this quadratic term which would have a behavior that also had a part here. And if you choose any particular value of energy, then you would have 3 particular roots to it. And that's as far as we went last time. So I guess the point I'm making is that all we're working with is Bernoulli's equation, nothing more than that. We're just writing it in a way that's convenient for us in terms of a flow rate, which doesn't change as we go up or downstream, and with the value of this height, which is substituted for the pressure head term, which is just this component. If we do that, we can define behavior in terms of this expression here, which is one that we will use in some way, or in the way above it. It's just as convenient. And it allows us to be able to explain why flow should occur in these two different behaviors. And that is, we could have a flow upstream which was quite, if we had a sluice gate, for instance, coming down, we could have flow which was this depth here and was flowing at some small flow rate here. We could have it relative to this bed here, which is 0, y equals 0. And this downstream flow would be controlled by this sluice gate, and these would be the two different regimes that we have. So that's basically what it's saying, nothing more than that. And it's all borne out by Bernoulli's equation, with the head loss term, which I guess is the energy equation, but basically Bernoulli's equation. So that's useful to us in trying to understand behaviors. So the other couple of things that we need to know is that the minimum energy for this particular flow rate, since this is energy along here, you could think about drawing, we're more used to thinking of things that are minima. If we draw this so that this is energy versus y, then I guess we have a curve that looks like this, right? This is just this same curve drawn differently. So if we minimize the amount of energy, which would be this point here, this is this point, which is the nose of this particular curve here. And so we could derive these things, but I'm not sure that I want to do that. I'll take the standard results. Maybe I'll slip back to this, to where it is, which is really not much further than we were, which is this. And we can have a couple of standard results. And the two standard results are that the place where this minimum energy exists, so it's right on the nose here, is this point here. And it turns out that that is a place where the Froude number is exactly equal to 1. So we said that this boundary between supercritical flow and subcritical flow, the physical explanation of it was that at supercritical flow, the flow is moving downstream faster than the celerity wave velocity. So like a drowning person flapping in the water, if you're trying to signal by sending a wave, it never gets to the recipient upstream of you. So there's no information sent upstream. So the point of the flow, the flow rate in the river that gives you that is this value, f equals 1. At places where it is subcritical, the Froude number is less than 1, because it's the ratio, by definition. This is the flow rate, this is the celerity wave magnitude. So if the flow rate is faster, then it's bigger than the 1. And so here, the Froude number is greater than 1. Here, it's exactly equal to 1. So as you move along this trajectory for this particular flow regime, as the depths change, then it goes from subcritical, a deep, slow flow, to a shallow, very fast flow. And the regimes change. So it's like the hydraulic jump that we've talked about. And so I won't go through the derivation of that, but we have that. Then this is the derivation here. And I guess the other term is that the minimum energy is also related to this critical velocity. So if you like to think about it, this nose is the critical location. And so the critical depth of flow is equal to 3 halves of yc. So this is E min is equal to 3 over 2 yc. And yc is the critical depth at which Froude number is 1, just by definition of this behavior. So those are some of the behaviors that we're interested in. Oh, I didn't know that. Where am I writing? Okay, can't find it. I think it's, where is it? Just after this one. So this is our interest in being able to judge this behavior. So it's pretty clear that if we have a geometry that we've talked about like this, where we control exactly what the flow depths are upstream and downstream, that we're sitting on here. If we don't have this constriction in the flow, and we get this change in behavior, for instance with a hydraulic jump, then the behavior that we get is controlled really by being able to move around this particular geometry, because this is for any constant flow rate that we have. And if we keep that flow rate, then we have to always remain on this curve. So the other thing that we can talk about is that in this particular case, what we're going to do is we're going to consider two cases. And so the two cases are this. The first is where it is Inviscid. So in other words, mu goes to 0, therefore the energy grade line SF goes to 0. And in that particular case, what we can do is we can write the expressions for the energy being constant between upstream and downstream plus this. So in other words, this term would disappear, and we'd be left with E1 plus Z1 equals E2 plus Z2. And so that's one of the cases that we're dealing with. The other case is where mu is not equal, not equal to 0. And so in that particular case, the energy upstream for a flat bed, which is the only one we'll look at, is not equal to the energy downstream. And we need an extra expression to be able to constrain flow. And this is the behavior that we have. So this would be for what we've called gradually varying flows, GVF. And this would be for what we've called rapidly varying flows, which we won't do in any great detail, but this is basically the hydraulic jump. So in other words, where a very fast, thin flow all of a sudden jumps into this very deep but slow flow, which kayakers roll down the front of, which we've looked at in terms of the video. So those are the two behaviors that we'll deal with. The first one is the easiest one, and it might be as far as we get, which is fine. But this is basically the behavior that we'll look at. So this is one geometry. This is one of the examples in the book. So it's useful to have it in the book because you can go back to look at it if you don't understand exactly what we're talking about here. Or I can't imagine that would be the case, of course. But this is the idea. So you have a flow that has a depth of 2.3 feet. I apologize for the imperial units or English units. And the question is, what happens if instead of having a horizontal flow bed, in which case it would just keep on trucking at 2.3 feet, if you have a ramp in that bed? And that ramp allows you to lift yourself up to half a foot above the existing height. We know that, and actually you've looked at an example using just Bernoulli's equation, that if you write Bernoulli's between the upstream and the downstream locations, you'd expect that the surface would have a dimple in it because it has to flow faster here because the cross-sectional area is slower. You can do the calculation with Bernoulli to show that it can't follow this exact contour of going up 0.5 of a foot because it doesn't satisfy both continuity and Bernoulli at the same time if the head loss is 0. And so we know that it would have a dimple. And so the question is, how do we calculate exactly how that flow would change? Would it change, for instance, from being maybe subcritical upstream to being supercritical downstream? And if not, what are the conditions that we have to apply to do that? So what we need to do is we know the flow rate, which is this. We know the upstream depth. And so presumably we can calculate energy being equal to y plus q squared over 2g y squared. So we could choose depths of y, which would give us the ability to draw this figure, and we'd end up with a curve that is this. This is the curve that results from this particular flow rate. And so if we look at point 1, which is a depth of 2.3 feet, then 2.3 feet is right here. And so if we look at 2.3 feet, then we know exactly that the energy associated with that flow is going to be this magnitude here, which is 2.4 feet also, right? These units have to be the same because this is length. This has to be length as well from homogeneity of dimensions. We know from our overall writing of Bernoulli's equation, which is this, that these have to be the conditions both upstream and downstream. So in other words, point 2 and point 1. And it's really represented by this curve here. We know that if it's inviscid, then there are no losses in our system. So this is 0, and so we're just dealing with this. And so what we could do is we could write the fact more conveniently that we could write E1 plus Z1 minus C2 is equal to E2. This is the energy that exists downstream. And so if we know we're sitting at this point here, at this depth and this particular energy, we know the energy E1 has to be equal to 2.4 feet in this particular case. Strange, not units of energy, but it's a proxy for energy. Then if we look at the difference between this half-foot change, then what we're going to do is we're going to reduce this amount by 0.5. And if we do that, then we know that we are at, did I overshoot it here? This is 0.5. 2.4 minus 0.5 is 1.9. And so this is the amount, the depth that would exist at that particular point. Just less than 2 feet depth, or a value of y of 2 feet, height of y of 2 feet. And so that's fine. So that means that to get from this point to here, it could, of course, also be 2 prime. But to get to 2 prime, we can only get there not by going just across here. We have to actually, because the flow rate in going from upstream to downstream is always this value of whatever, 5.75 cubic feet squared per second, we can't get to this point 2 prime unless we go around this nose. And so the question is, how do we get to be a very shallow flow downstream? The only way we can do it is if we have a bump in the ground that takes us up from 2.4 feet all the way to this magnitude here, which is at this nose, it turns out to be 1.51. So the difference between 2.4 and 0.51 is 0.89. So this amount here is 0.89 feet. And so instead of going up just 0.5, if you have a ramp that actually takes you up the full amount, then this would get you to this nose here, exactly here. So at this section here, it would be flowing at this particular depth and at this particular energy, which would give us a particular flow velocity because you know the cross-sectional area. And as it goes downstream from this, then the energy changes, and so now you are able to get around this nose and get to this second point, which would be this depth, which is this smaller amount here, which is 2 prime. And so the two depths that we have potentially would be this depth y2, which is this point here, which is differing by 0.5 height between upstream and downstream, and this depth here, which is this point here. So it's maybe not so straightforward, but that's basically it. So the idea is that this line represents one particular flow rate that we're constraining. It has to be the flow rate between upstream and downstream because we're prescribing it as such and it can't accumulate. And that if we know the conditions upstream, then we can predict the conditions downstream as well. So that's it. And so I think there's a lot of complicated math in here. We're doing some things, but that's basically what's going on. The alternate scenario would be if you have it acts in reverse. It's basically the same idea, and if you had instead a much higher velocity flow occurring upstream, again with the same flow rate, Q equals constant. And as a function of this, you could calculate as a function if you know this, and if you also know V1, you also know Q. If you know both Q and you know Y, you have enough to be able to calculate energy, which is just equal to Y plus Q squared over 2GY squared. You can always do that. If you know Q, you can choose a whole bunch of different values of Y, and you get a curve like this. If you know what the upstream behavior is, in this particular case, I guess this is Y1, then you can find exactly where you are on this curve, and you end up at point number 1. And then you can say what happens now if you put a bump in the bed of 0.5 feet. And so 0.5 feet changes the energy just because E1 plus Z1 equals E2 plus C2. And so if you want to calculate this, you know that the drop between these two from Z1 minus Z2, and so you know the change in energy. This one is energy 1, and this has to be energy 2. Energy 2 has two potential roots. It actually has 3 roots, of course, right? One here, and maybe one down here. Don't care about the imaginary one, but we know that if we want it to be able to change behavior, then as we go up this bump, then it actually gets to be a deeper flow, and this is the magnitude of the depth that we get for that flow. If we want to be able to get up here, then what we have to do is we have to have a bump in here which is equal to this total height here. Without putting a number on it, I can call this W1 for no particular reason, and this bump here would be W1. And if we do that, then at this nose, then the Froude number here is exactly equal to 1, because we're at this point here by definition. The depth here would be YW, which would be this depth above here. I don't know what it would be. It would be this height above here. This would be YW. And then as it goes downstream, then I guess it would get even deeper, right? It would go up here, and it would be this pillow up here. And this would be this magnitude here, which would be Y2 prime, which is this here. So that's it. So it seems, I don't know if I think it's good to look at these things graphically as to what they are. But the basic idea is that for a single flow rate, you'll always have a single nose-like diagram, and it won't change. You can figure out exactly what this diagram is just by plotting this term here for a whole bunch of values of y, choosing a bunch of different values of y. And then once you have that, and you know the ordinates of your upstream flow, which are either a velocity or a flow rate, Q, and a depth, you get 1 point, and then all the other changes are based on an energy change in this particular case. Because we've thrown away this other term, which is HL, which is 0, and HL is just the slope of the energy grade line, which is, in this case, is flat. Okay, so that's it. And so we can make it more complicated by looking at different things, but well, maybe this diagram kind of epitomizes exactly the case. So if you have a flow that is a given flow rate, and if you're sitting here, then by definition, everywhere above this nose is a Froude number which is greater than 1. It's subcritical. Everywhere below this number is a Froude number which is less than 1. If it's subcritical, then as you change the elevation of the bed by this amount, for want of a better number, W, since we used it before, then you can change the depth of flow, which goes from deep to shallow as you move down here. If you start off, if you want to be able to go, if you start off shallow and you have the same rise, then you start off shallow, you go up the same amount here, this is also W. Then again you go from here to this new energy, and this is the new depth that you have here. So in other words, you go from shallow to deeper. Actually, you're subcritical, and you're still subcritical because you're still on this side of the Froude number equal to 1. It's at y sub c, right? This is y sub c here. If you start off supercritical, flowing less than a Froude number of 1, as you go up this bump, you still remain supercritical because you can't get to this other side. You could be in this condition, but you can't physically get there. The only way you can get there is if you start off subcritical and you put a bump in it here to be able to make sure that you get exactly to this nose, tip of the nose, and then once you go downstream, you've transited and you're able to get across. So that's kind of the physical description of it. All right? Have a look at, I think the book does a decent job, if I haven't done a decent job of explaining it. And it's a bit complicated, but that's basically the idea. So the workflow is figure out from upstream if you have a velocity, or if you have a flow rate, or if you have a volumetric flow rate. If you upstream you have a y, then those both give you the ability to calculate E is equal to y plus q squared, right? Q squared over 2g y squared. Once you have that for a given flow rate, then you can do all these other things that we've talked about. You need to remember that the nose of this is where it transits from subcritical to supercritical. It happens to have the minimum energy at this point, and the value of this depth is defined as a function of minimum energy as well. And so you know the ordinates of that point are that E min is equal to 3/2 of yc. Kind of a standard result that we've used. Okay. All right. So you can look through that. There are some other. Yeah, I'm not going to talk about these other things. So you can figure out whether there's a question on the exam based on how we're going through this for this year. All right. So we made the point before, which is perhaps so. Yeah. So the other point we've made was that there are two kinds of behaviors that we've dealt with here. The one we've talked about so far has been this so-called Inviscid one, where we've assumed that Bernoulli's law really is Bernoulli's law without the HL term. So in other words, head loss is 0, in which case we're able to accommodate the behaviors we've talked about. The other term is where there is head loss in the system. So where head loss is not equal to 0. And briefly, it's not so important to us, briefly we'll talk about that. And so now what happens, it turns out that no longer, if the head loss is 0, can we assume that the energy upstream and downstream is the same. And the reason for that, as we know, is that if we look at this cross-section, if it's inviscid, then the energy grade line has to be absolutely horizontal. And so the energy at point 2 and the energy at point 1 have to be the same. In other words, SF is 0. And of course, that is the case where Bernoulli acts. There's no head losses in the system. It turns out that if we want to look at things like hydraulic jumps, we can't get away with that approximation. And so we have to account for the fact that there's a head loss in the system. If there's a head loss in the system, then the energy at point number 2 is going to be this lower energy than it is at point 1 because it has a gradient to it. And so because of that, everything that we've done so far using Bernoulli, using this expression, we've been able to take E1 and E2 as well as equivalent to each other when we have a flat bed. So it's not so much that they're equivalent to each other, but for our particular conditions with a flat bed, they would be equivalent to each other. Now we're not able to do that. So the ramifications of that are that if we draw a diagram like this, we've always been able to go down upstream and downstream through these two places. But if the energy is not constant as we go from upstream to downstream, then this is perhaps the trajectory that we should be taking. Yeah? And so I don't intend to go through these derivations, but except to note that for a hydraulic jump, we can do the same things that we've done before. We can look at balancing momentum in this control volume, which is outlined by this green box here. We have a force upstream, a force downstream, velocities, and we can balance them. This is sum of forces. Oops. You recognize this expression as being sum of forces is equal to velocity times mass flow rate. It turns out to look something like this when it comes out. We can define another term that instead of being energy, uppercase E that we've used today, we can use a different term which is momentum, which is from this expression, which is a slightly different expression, y squared rather than y. We can apply continuity, and we can apply Bernoulli's equation. And so if we use these, you see that the energy equation, this is basically energy is equal to y plus q squared over 2gy squared. It's what we've been talking about today, right? And so this term is E1. This term is E2. We've thrown away z, the elevation change, because it's a flat bed, but that's what this term is. This is the viscous term. And so the point is that instead of just having an energy term, which we know what to do with, we now have a momentum term which is kind of similar. It's a function of the flow rate, and it's a function of y as well. The only two terms that exist in this. So we could do the same thing. We could draw a diagram now which is the energy diagram, which we've talked about before, which has this, for a given flow rate, it has this plot with a minimum energy here. And we could also plot this term for momentum. We know the flow rate, we know the depths, choose depths, and we get different values of m, and we can look at this. And it turns out that if we're looking at a hydraulic jump, then because there's energy loss in our system, we can't choose a place where we go across this curve at a single location. But what is conserved within the system is momentum is conserved. Energy is not conserved because it's being used up by frictional losses, but momentum is being conserved. And so if we know what the upstream depth is, and if we're able to create this curve for quote-unquote momentum, uppercase M, this term here, then we have a curve. We know if we're upstream that if the flow rate, the flow depth is like this, and it's flowing very quickly, this has to be a fast flow because of continuity. This has to be a slower flow because of continuity. So we know that we're at this point here. If we know that momentum is conserved, then we know that we're at this point here. And so we can use conservation of momentum in these particular cases to be able to figure out exactly what this is. And so this would be the depth that we'd predict for being downstream relative to this hydraulic jump which is triggered. And if we looked at the magnitudes for what the energy locations would be, then this would be the point on the energy curve, this would be the other point on the energy curve, and I guess by definition this is the amount of energy which is being eaten up by the system. And I suppose since this is a length, this is the same as equal to, this is the same as what we've called h sub L. And you can rationalize that from what we've said about the flow downstream. So that's, I'll probably leave it there. And so we can calculate exactly what these pillows on the New River or wherever that video was in West Virginia as to what exactly the geometries of these would be. And so we'll leave it at that.